So for our second video, we're actually going to kind of take a closer look at this separation of variables method. Now, for those of you who maybe were watching the first video and thinking, wait a minute, you can just do that? You can just multiply both sides by dt and move it to the other side, and then you can integrate like that, just like suddenly appears an integral symbol? Technically, no. What I did right here in these two steps is kind of breaking the rules. The rules say whatever you do to one side, you do to the other. And if I'm going to integrate one side, then I'd be integrating the other side with respect to the same variable. So I can't just willy-nilly decide to move those integrands like that, or the differentials like that. So at the top of the next page, it says something should feel a little uncomfortable there. And so it really doesn't make sense to split up dy dt by multiplying by dt, but it does work. And so we're going to do a real quick look at why does this work. So we're going to consider a generic, what we're calling a generic separable differential equation. Now, if you remember, what made it separable was we were able to move the y's to one side and move the functions of t by itself to the other. And so notice what we have right here is the multiplication. This is always multiplication. And it's got to be a single term, right, of multiplication of two factors. One is going to be in terms of the independent variable, and one is going to be in terms of the dependent variable. Right? That's the only way this method works. Separable differential equations are really, really special. It can't be some function of t times y of t plus 3, right? If the plus 3 were there, boom, all bets are off. We can't do it. So what we're going to do is we're going to take this kind of generic situation and we're going to kind of spell it out and see how this works. And so we're going to start with our dy dt equals g of t times y of t. And remember, g of t, this is just, it could be t squared, it could be t, it could be 2t, it could be sine of t, whatever, but it's just a function of t. There's no y in it. There's no other variable there. And so I'm just going to divide both sides by y of t, or multiply by 1 over y of t. And so I have 1 over y of t times dy dt equals g of t. So far, so good. But off to the side, I want you to remember that, I'm just going to add a little note here, recall that dy dt really is the same thing as saying the derivative with respect to t of the function y of t, right? And so we're going to use that to our advantage. And so thanks to the chain rule, we wind up getting something that works. We're going to integrate both sides, but we're going to integrate both sides with respect to t. So I'm going to integrate this side, 1 over y of t times dy dt. All of that, I'm going to integrate that with respect to t, and I'm going to integrate the other side with respect to t. This is technically following the rules, right? Because whatever you do to one side, integrate with respect to t, I have to do to the other side. So the key here is we're integrating with respect to t on both sides. With respect to, sorry, the t variable, right? We could have integrated both sides with respect to y, but it wouldn't be terribly helpful for us. Because if you notice that on the left-hand side, thanks to the chain rule, this thing becomes something else. We're integrating the derivative of y with respect to t with respect to t. And so what we wind up with on the left-hand side, this thing through the chain rule becomes the integral of 1 over y of t times the dt, and the dt kind of, they blow up, taking the derivative and then integrating with respect to the same variable. They sort of undo each other, and you're left with this, which is exactly what we jumped to. That was the conclusion that we jumped to. Now, it turns out this method always works for a separable differential equation. But notice, but it's got to be separable. If it's not a separable differential equation, all bets are off. So we've found an analytic method that always works as long as you're talking about a specific kind of differential equation, a separable differential equation. So let's take a look on the next page and see what happens. Oh, there's some notes up here. The idea is we don't have to do that again. We don't have to reprove that. Now that we know we can just jump to this conclusion, that's what we're going to do. So this works terrific for separable as long as it's separable. So this works great for separable differential equations, which means we can always use this method. Now, notice, it doesn't say that the integral that you wind up with is going to be easy to solve. It doesn't say anything about whether the integral itself is going to be easy, whether the left side or the right side integrals are going to be doable, right? You might have to integrate using by parts methods. You might have to integrate doing a trig substitution. Or you might just jump on Maple and go, hey, Maple, please help me solve this. Doesn't mean that the integral is easy, but the method works. So let's take a look at this one. Here's an example. We've got y prime equals x times y. Now, notice we can't tell directly that this is the derivative of y with respect to x, but the context would sort of imply, right? So I'm going to make a little note here and say context implies y prime is the same thing as dy over dx, right? When you don't have the differentials written out plainly for you, we need to be able to imply or infer what's going on. So notice it's y prime equals x times y, and notice that from before we see right here this is the multiplication of two factors, and there's only one term on this side. And one of them is with respect to, or in terms of x, and then one is with respect to y. So that means that we can use our separation of variables. Yay! And by the way, at this point in time, if we couldn't do separation of variables, we're just dead in the water. So let's see where this leads us. We're going to have dy dx, we'll start off with our original problem, equals x times y. Now I'm going to just use the cheat and say I'm going to divide by y and multiply by dx, and I'm left with dy over y equals x dx, and we're integrating both sides. So we just jump right to that. And these are both integrals that are not hard for us. The integral of dy over y is, if you remember, the natural log of, technically it's the natural log of the absolute value of y, plus a constant, call it c1. And the right-hand side is 1/2 x squared plus another constant, c2. So we're going to combine our constants. We're trying to solve this thing for y. We've got natural log of the absolute value of y equals 1/2 x squared plus c3. And again, I'm keeping track of my constants here. This is c2 minus c1. And now I need to figure out how to get y by itself, but it's inside of a natural log. So if you remember the techniques for being able to get something out of a log, the way you do that is you undo the logarithm. And so we're going to exponentiate. But we're going to do that to both sides. The entire side needs to be exponentiated. So on the left-hand side, we'll have e to the natural log of absolute value of y. And the right-hand side will have e to all this stuff, 1/2 x squared plus c3. Now, if it's been a while since you've played around with exponentials, you may have forgotten that when you have something like I'm going to put a little recall notice over here. Recall that e to the a plus b is the same thing as e to the a times e to the b. That's the way powers work. And so we can use that to our advantage on this side and say, oh, it's e to the this stuff times e to the C3. So we're going to spell that out. So this side, on this side, the other one that you should remember is e to the natural log of some stuff kind of falls away. E and natural log undo each other as base and power like this. And so we're going to be left with y, or absolute value of y, equals, on this side we've got e to the constant C3 times e to the 1/2 x squared. Now, e to the power up here, because if we're talking real numbers, there's no way that e to the some power could be negative. So this side of the equation, I don't really need the absolute value. The absolute value is going to work itself out just fine, because everything over here has to be positive in the real number realm. So we get y equals e to a constant is itself a constant. So I'm going to call that C4 times e to the 1/2 x squared. And so what we have, let me make a little note here, C4 is equal to c, or e to the C3 power. Right? And so what we have now is the general solution for y of t. Oops. This is the general solution. Y of t. And so we can verify that, again, by substitution, or we can verify that in Maple. So let's take a look at what that looks like in Maple. So let me switch over to Maple here, and we'll type this in, and we'll say, hey, Maple, will you desolve for us? Oops, got to back it up. Changed cases on me here. Desolve, and I'm going to type it in this way. I'm going to type in y prime equals x times y. And we have to say x times y, or else it'll think xy is a variable. So what is the solution for y prime equals x times y? And notice, Maple doesn't have any trouble with that. It automatically assumes y prime is in terms of x. The default for Maple is y prime is y of x, or it's dy dx. So notice, this should look familiar. Sure enough, we have a constant out front times e to the x squared over 2. So it agrees completely with our solution, and that's a good thing. We like that. So if we take a look at the next page, we can get going on the next example. And what I'm going to do is we're going to solve this on paper, and then I'm going to ask you guys to check it. And I'll start the next video by taking a look at our solution in Maple. So let's solve this thing real quick. We know how to do this now with our separation of variables solution. So we can take a look at this and say, aha, the right-hand side is just y squared. There's no function of t. Well, technically there is, because technically it's times 1. And you might think, oh, that's kind of cheeky, that's sneaky, but it's always times 1. So you can always think of it as times a function of t if you need to. So that means we can rethink this equation as the integral of, if I divide both sides by y squared, dy over y squared, and the right-hand side is just the integral of 1 dt. Or just the integral of dt, if you want to think of it that way. This side, this is not the natural log. That is the integral of y to the -2 power, which when we integrate it, we get -1 over y plus a constant. And the right-hand side, we're going to have just plain old t plus another constant. And we can keep going with this. We have I'm going to move the constants to the other side, and I'm going to be also multiply by -1. So I get this, 1 over y equals -t plus C3. And now in this case, C3 is what we get when we multiply by -1, C2 minus C1. And again, you might be thinking, do we really need to keep track of all this? The answer is, while we're still getting used to this, yes, because we want to be able to double check at any point. Last but not least, if I want to solve this thing for y, the easiest way is to think about inverting this side, which means I have to invert this entire side. So I'd have y of t, or just y, equals 1 over everything here, negative t plus c3. And this becomes my general solution. And so let's actually, you know what, I'm going to change my mind. Let's verify this using our resubstitution technique here. Verify with substitution. And so when I say verify with substitution, that means I should be able to take this general solution and throw it back into my differential equation. So I should be able to say, what happens when I take the derivative with respect to time of that solution there, 1 over negative t plus a constant? Is that in fact equal to the solution itself squared? And so this is 1 over negative t plus a constant. And so the right-hand side's pretty easy. We're just going to wind up with 1 over quantity negative t plus c3 squared, right? And on the right-hand side, when we take the derivative of this thing, we wind up with this thing to the negative 1 power. And so the negative 1 power gives us the negative 2 power when we take the derivative. So this thing is going to be to the second power. And sure enough, it works. We wind up with the solution. So we wind up with a solution that checks out when we take the derivative on the left side and when we square it on the right-hand side. So the question is, what does Maple say? And so I'm going to pop over to Maple real quick. We got just a little bit of time. I'll just type this into Maple real quick just to verify. Dsolve. And this time I'm actually in the dsolve, I'm going to use a different coding. Rather than use the palette over here, I'm going to use the coding Diff for differential. I'm going to take the derivative, differentiate y of t with respect to t. Notice the nomenclature there. I'm saying take the derivative of y of t with respect to t. And this thing is equal to y squared, but it's y of t squared. And you can put, if you're worried about it, you can put parentheses around the y of t, just so that we know what we're squaring here. But when I take the derivative of this, I should get something that looks very similar to what I had. And sure enough, I get almost exactly the same thing, except it calls it C1 instead of C3. So it checks out. The only problem is that every single one of these solutions right here, if you were to imagine what these look like, they look like the graph of, if you imagine 1 over negative x, something like this, you wind up with a solution that looks like this. And of course, if I throw in something in here plus 2, then I take the solution, I just shift it over by 2 units. If I subtract 1 or subtract 2, I shift it to the left 2 units. So you should recognize that this thing that we just found as the general solution has an infinite number of curves that are all the same solution. But what's interesting is when you take a look at the graph of all the solutions, there's one solution on here that's not something that we would have predicted. You can see all these different curves like this, and they all go together. They're all different families, but there is one curve that rides right along the axis right here. That means that y equals 0 is a solution. But how can that be? How can you get y equals 0 from this equation right here? What would you have to do to t, or what would you have to do to c, the constant, to wind up with y of t equals 0? And the answer is, just like we could shift left and right by using different numbers in here, if you imagine throwing something in there that's really, really, really big, positive or negative, it's going to shift your graph to the left or to the right very far. And so if you imagine shifting infinitely far, that's what it means to have y equals 0 as a solution. So when we first saw this problem on this page, y equals 0 is an equilibrium solution. But it's not obvious. From the separation of variables. Right? You would not have predicted y equals 0 when you came up with this, or at least most people wouldn't. So it's a really interesting case where you think you can see all the solutions because you solve it analytically, but the most obvious one, the equilibrium solution, where's the derivative equal to 0? Well, when y is equal to 0. That solution is not incredibly obvious through our analytic methods. So we're going to stop here, and we'll take a look at, in the next video, when can we use this and when is this a problem? When is this separation of variables a problem?